We figured out how you make the X-rays from our X-ray light bulb or X-ray tube. And then once we have these X-rays labeled here called incident photons, we basically have two major ways of those X-rays interacting with matter or with the patient. Okay. The photoelectric effect, in which the X-ray knocks an electron off of the atom. It's called the photoelectron. And then you can have a characteristic radiation come out of that atom, or you can have an Auger electron come out. They're both, as an electron drops down into from a higher orbit down into the place from which the photoelectron was ejected, energy comes out of the system either as characteristic radiation as a photon or an Auger electron. Both of those get lumped in as photoelectric effect. Compton scattering is the other major way that the incident X-rays that we've created get absorbed or deflected by the patient. Many of these, they undergo a scattering with the scattering angle is not, say, 45 degrees or 90 degrees, such that it totally exits the patient. It's a smaller angle at which the Compton photon that results from this interaction of our incident photon comes close to an electron and sort of reflects off of it at some angle. And then as that Compton photon travels to our detector, one hopes that it's at a sufficient angle that it hits what's called the anti-scatter grid and gets absorbed, right? Yes, question.
So doesn't the anode fire electron, not photon?
Oh, what are we talking about here now? The anode?
Yeah,
Oh, okay. Are we going back to the X-ray tube?
like totally different.
Yeah, this is different. So remember, we did two interactions with matter. We've just recently done two. The first one was we boil electrons off of a cathode and accelerate them towards a target, which is the anode. And that collision creates these X-rays that we've labeled here as incident photon. Okay. So the diagram looks the same because it's an electron hitting matter and there's some kind of collision and scatter and things like that. Once that's done and we have a beam of X-rays coming out of our target, then we look at this. And so these atoms are actually in the patient, right? So they're part of the target, and we're going to cast a shadow. And the shadow will be, an X-ray shadow. So, yeah.
Sorry, the characteristic radiation in the first graph, is it a photon too?
Yes. This is the characteristic radiation is a photon. Okay. And what are the relative probabilities of these two events occurring? These formulas give those probabilities, or the cross-sectional probability. So if I have an incident X-ray creating a photoelectron with a photoelectric effect, this goes as the fourth power of the atomic number of the atom. And that's because we have more and more electrons. As the atomic number goes up, the cloud of electrons that the photons can interact with goes up, and increases the probability of this happening by a large factor with atomic number, power 4. It also, this type of interaction, the probability of it occurring decreases quite significantly with energy. So as the energy of the incident X-ray goes up, the amount or the percentage, say, of interactions that are photoelectric, or the probability of this occurring, goes down precipitously. Okay. And for the Compton interaction, where we just reflect or have an interaction with an electron and come off with a Compton photon and an ejected electron, this is how the probability of that changes. It too goes up with atomic number, sort of density of electrons in the sample or the patient, but not as quickly, right? And the interesting thing, it's relatively constant with energy. Okay, so regardless of the energy of this X-ray, the probability of having a Compton event is about the same. And we can look at a graph that shows this is the mass attenuation coefficient, probably in water. Does it say here? Yeah, and it's the component of that attenuation that is produced by either the photoelectric effect or the Compton effect. So a high mass attenuation coefficient means a lot of X-rays get absorbed. A low mass attenuation coefficient means the X-rays pass through more easily. And we are interested in X-rays that have an energy here between, say, 20 keV and 120 or 140 keV. Somewhere in that range is what we're interested in for X-ray imaging. This is 1 MeV. So this is up here is like gamma rays up here, right? So we actually have pair production occurring here with a photon that has this much energy. You can actually make an electron and a positron spontaneously, like matter. That photon can turn into matter, right? So if you have enough energy up here. But we're interested in these X-rays between, say, 30 keV and 140 keV, something like that. If we look at the photoelectric curve, we see at very low energies a very high amount of X-ray absorption or a large mass attenuation coefficient, right? And then across the range of energies that we deal with in X-ray imaging, that changes by decades. As you can see, it's changing. This is a log scale. There's a factor of 10. Here's a factor of 100, a factor of 1,000, right? So it is dropping precipitously with energy. This curve gives the probability or the mass attenuation coefficient from purely Compton scattering. And as you can see, over our energy range, it is pretty constant. Okay. So that's just happening all the time for all energies at 30 keV to 120 keV. Interestingly, this gives us an opportunity, right? If we could make an image, let's make 2 images of the patient. We'll make one image, say, at 40 keV. We'll use electrons that are at this energy. Well, we're going to get this much photoelectric effect, right, from that beam, and this much Compton. And now we crank up the energy, take another image right away of the same patient at, say, 140 keV, and now we have virtually no photoelectric effect, but we still have the same amount of Compton. So now we have 2 images that are quite different, right? So one image is basically a Compton scatter image, and one is a photoelectric plus Compton image, right? So with those 2 images, I now can create a synthetic image that is some kind of combination of those two to bring out different contrast in different tissues. Recall that, I think we'll probably look at it right now, different tissues have different mass attenuation coefficients. Okay, that's how we have the contrast between them. So let's review our system that we've got here. We have a source of X-rays, and this is that cathode boiling off electrons, hitting an anode target, creating a beam of X-rays. It actually creates X-rays in all directions, but we're just going to allow them to exit this box through this hole. Okay, so they're all just coming out here. Ideally, all of the X-rays would emanate from a single mathematical point, so that when I came down here, I know exactly from where that X-ray came from, exactly. Unfortunately, we would burn up our target if we did that, so it usually comes from a rectangle, right? And so that adds to a bit of blurring on the imaging because the X-ray might have come from over here, or it could have come from over here, right? So there's a bit of blur. Yeah, question?
Question about 2 slides ago about the X-ray interaction with matter.
Okay.
So I was wondering, it says on the screen that Compton scattering dominates at high or low atomic numbers, but it seems like the atomic number at the top is proportional to the amount of Compton scattering.
Uh, well, that, so at low atomic numbers, it's saying Compton scattering. Where are we reading this? I'm sorry. Right here? I see. Not much contrast. Oh, okay. Yeah, because here, with this effect here, that you would have the probability of a interaction occurring at z to the fourth with photoelectric. So as the atomic number gets bigger, this probability gets very, very high, right, compared to the Compton. That's what that's saying. Right. Right.
The Compton is not having like much of an effect on the actual probability because it's not being like to the fourth power is like.
Right. Well, the ratio, just the amount of photoelectric events that would occur for a low atomic number thing versus Compton, and then you go to a high atomic number thing, and the photoelectric is going to take off and be the dominant event. Don't get that confused with the energy here, right? That's just the energy of the photon, not the Z of the actual element, right? We'll get to a chart where we have different Z's, actually different elements. Okay.
Sorry, another question regarding the energy. It's the first effect is proportional to the inverse of the energy to the power 3, right? Something like that.
Yep.
Which means with higher frequency, we get less of photoelectric effect.
Correct. Correct.
Why? Like, isn't it like if I imagine a more frequent way, is it more probable to impact? Why does that happen?
That's a great question. Why this is mu to the third power? I do not know. Like is my answer to that question. Why it would go as to the third power? I'll look it up.
Why is it inverse inverse proportional? Why isn't it like just proportional to the frequency?
Right.
When I increase the frequency,
I don't know. I'm going to say I don't know to all those because these two formula, I don't know the derivation of that formula, but that would be where we'd find out that answer. We can look at the derivation of these two formulas and try and figure it out. All right. Sorry. Don't know. Yeah.
20 and 100. But the area just before that also has like a greater photoelectric effect.
Yes. Because if you get down there, the problem about making images down there is none of them get out of your sample. So that you shoot these, say we put 10 keV photons into the sample, nothing's coming out. So your image will always be the same, right? So you have to have enough penetration to have some of the photons survive, right? Ideally, large, like 50% of them would survive or something like that. Yeah. Well, it's because as you saw, different materials have different amounts of photoelectric effect based on their Z number. And so you can make a photoelectric effect image and you can make a Compton image, right? So basically your photoelectric effect probably is a Z image, right? Okay, cool. So we've got our small rectangle, ideally a spot, but it's not. We filter out the X-ray photons that are below a threshold energy because they're just going to get dumped in the patient and not produce any contrast. And so now we have a beam of X-rays coming down here and they hit the patient here. They get differentially absorbed on their pathway through the patient, right? And if there's bone in the way, they're going to get absorbed more than if there isn't, et cetera. And then goes through the tabletop. This is the anti-scatter grid, okay? So that if my photon comes through here and it has a Compton interaction and then shoots off this way, when it hits the anti-scatter grid, it will be absorbed. It won't cause a flash down here in my detector. So let's say I move through the patient, I survive my travels through the patient, I get through the anti-scatter grid, I hit this stuff, and this is a screen. It's usually some kind of phosphor screen that lights up when X-rays interact with the material in it, causes a flash. And in the old days, this just used to be a piece of photographic film. And that flash would cause a chemical reaction in there, just like taking a photograph, right? Yeah.
Filtering, the X-rays again?
It's to get rid of the low energy X-rays that would have no chance of getting out of the patient.
Okay,
So they would all just dump into the patient and none of them would get through.
so they would get absorbed and then you would be able to see like.
They don't cause any contrast. All they cause is dose, right? So they just get rid of them. And you can, oftentimes the filter is aluminum or copper, but depending on what you use, you will change the energy spectrum of your beam, right? So you could weight your energy spectrum to high energies or lower energies. So that, yeah. It actually, here, it's not a big deal. I mean, wires absorb X-rays very well, so they show up as very bright objects in the image. They will generate artifact in CT because they absorb so much of the X-rays. You oftentimes, behind a device like that, you will get no X-rays hitting the detector. And so as you do your projections, it becomes a very dominant structure. But for the most part, you can get around those problems. Unlike magnetic resonance, where you have huge RF energy in the field and electronics in a pacemaker. And so those two things sometimes do not mix, right? You have to have a specially designed pacemaker so that it's not sensitive to the radio frequency energy. And it doesn't have ferromagnetic materials in it. Okay, so we're going to write down some equations to look at these concepts. The intensity that we're going to detect on our detector, this will go up if we have more X-rays and down if we have less. The intensity, it's going to be proportional to the photon fluence. That means how many photons are coming at the detector. Remember, I can dial up my current on my X-ray tube and just make more photons come through. That would change this term, the photon fluence. And it's proportional to the energy. So higher energy X-rays, when they hit the target, will make a bigger intensity, a bigger splash, right? And in terms of the photon fluence, it's usually given in number of photons per unit time per unit area. Okay, just those are the units of the photon fluence. And so we've been talking a lot about the energy of the X-rays that we are shooting through the patient. Let's say we set our voltage on our X-ray tube to 100 kilovolts. That means the highest energy X-ray I can have coming out of that tube is 100 keV, kilo electron volts, right? Because it's an electron accelerating through there. And so that's the highest energy I can have. And then this is the relative number of photons at all the other energies between that and zero. Okay, so it's just if you know what a probability density function is, this is like that. It's essentially, the ratio of photons. And you can see this has a sort of a peak somewhere around 50 keV, something like that, right? In order to get the entire fluence, we can integrate all of the photons coming out at all energies. So this curve we're going to call S as a function of E, right? It's the relative numbers. And I can just integrate under that curve to get the total number of photons per unit time, per unit area coming out of my tube. So then I multiply that by energy and I get an intensity, right? And it's just how many X-rays at this energy are coming through is governed by the probability density function, or this density function SE. So I just integrate under that probability density function times the energy, and that gives me my intensity. Okay.
Right.
It also gives you the mean value of this.
Maybe it's a dumb question, but why isn't it one the area under the curve if it's a probability thing?
Well, we can set it to 1. Sure, I can set but here's the deal. So if I set this one to 1, okay, so if I do my interval, I just have some unit and I say that's 1. Then I crank my kilovolts to this. Now, do I set this to 1? Right? The big one? Probably not. I want that to be 1.4 or something, right? So their relative numbers depend. But it is, if you wanted to say, hey, let's set everything such that at 100 keV, this thing is going to integrate out to 1, then we could do it that way. It's kind of arbitrary in a way. Yeah.
Why is it that if you increase the X-ray photon energy past a certain point, the relative X-ray intensity goes down?
If I increase the photon energy, I'm going this way, right? You're saying, oh, as I go this way, why does this go down?
Yeah, because it goes up for a bit and then it goes
Right.
down.
Right. Oh, okay. Good question. The actual question is, why does it go down on this side? Right. So if it's just the probability of a Compton interaction at 120 keV is very small. When I put my tube to 120, I do get some photons that have like complete elastic, like 180-degree collisions with electrons, but not many. Most of those collisions are at angles that shoot the Compton photon off at a smaller angle, right? And the relative probability of those would just keep going up linearly, just like this, right? Unless we filtered out these low guys. So when you filter out the low guys, then the curve looks like this. If it was just pure physics and the relative probability of these different Compton interactions at different angles, it just goes up as a straight line. Okay.
Perfect.
Yeah, I mean, basically we'll see most of the time you just assume you're imaging with an energy that's kind of the mean value of this thing at 50 or 60 keV, right? And then you do all your physics based on that. We'll see that. Okay, so let's look at the attenuation, how you model it. This is a very heuristic explanation. It's very simple. If I have, say, 1,000 photons and they hit a target that's like 2 centimeters or maybe a centimeter of water, and what comes out the back end of this, what emerges from this thickness, this 1 centimeter of water, is 800 photons. 200 of them got absorbed, right? And then if I have this 800 photons now coming out and they hit the same dimension target, 1 centimeter of water, say, then again, I reduce this by 20%, 640 photons come out. If I do it again, 1 centimeter, 640, I take 20% of those out in interactions, 512 come out. So you can kind of see how this is going, right? And if we plotted that along this curve, that function is simply whatever the starting number of photons is multiplied by an exponential decay, right? That is linearly proportional to however long the distance is we've gone through times this thing called the linear attenuation coefficient. And that linear attenuation coefficient is particular to whatever is inside this target. If it's water, it has a certain value. If it's air, it has a different value. If it's bone, it has a different value, okay? So you can imagine with bone, I'd lose more than 20% of my photons through this, and this curve would be steeper. It would be a faster decaying exponential. Okay, so that's the concept of linear attenuation coefficient. The reason it's called linear is because if you look at it explained this way, if I have big N photons hitting my target, and my target is some delta X, then the number emerging from the target is just mu times big N times delta X. Yeah.
distributions, you said it depends on the object and we target it. So when we, so is it possible, like, how we determine like the coefficients?
Oh, you measure them.
You, so is that like the adjustable?
Nope, it's like water is water. And so if I put water in a scanner and I put x-rays through it and I measure how many x-rays come out the back, I can measure mu.
Arbitrary.
It's not arbitrary, it's just whatever God did, you know. That's right, it's like that's water. And then you have, you know, aluminum and copper and all that stuff they're empirical numbers. You could maybe derive them from first principles, but doubtful, right? And so basically there's a table it's called the National Institute of Standards and Technology, and they have books, now electronic books, that give all of these values for all different materials, right? And then if you're making a phantom, say you've got some resin that you're printing with and you make a 3D phantom, then you usually get the resin and make a nice little sample and shoot x-rays through it and see what its mu value is, right? It's a very prescient question. A CT image, in the end, when you put up a brightness map and you say, this is my CT image, it is a map of the mu values. That's what it is, right? It's linearly scaled, but it's linearly proportional to the mu values of what's in the sample. So we're going to make pictures of this thing, right, with CT. So when you set up the equation like this is why it's called a linear attenuation coefficient, right? It's a very simple relationship here. And from this equation, you can just derive, you know, using a simple first order differential equation like you've done 1,000 times for a beer warming up to room temperature or whatever. You get this equation and this is the solution. So you have a couple of things. You've got how many photons you start with going into the sample, right? And then the number that come out the back of the sample is proportional to the number you start with, e to the minus mu delta x, which is the thickness of the sample. And mu values, it turns out, you'll see, we'll show you a couple of them, and they're hard to remember, right? Because they're like 0.69134 or something like that for water, right? So an easier thing to remember is the half value layer. And so most people that work in X-ray imaging or CT know the half value layer for lots of different materials like water and muscle and lung and brain and all that kind of stuff. And so the half value layer, very simple concept, right? It's what is the delta X value I have to put here in order to create half of my photons being absorbed, okay? And so it basically is just mu, or the half value layer is 0.693 divided by mu, okay? It's easier to remember. So here's some example half value layers. And so after doing this, you will know kind of how things are going on in your patient in terms of how many photons are left, right? So let's look at the half value layer for muscle. It's going to be different for different energies, right? At low energies, 50% of the photons are gone by the time we've gone 1.8 centimeters into the patient or into the muscle, okay? So that's not that far, right? It's that much, right? So when I go in 2 centimeters, 50% of the photons are already gone, right? And then 4 centimeters, 50% more are gone. That's right. So it goes like that. So that's down at 30 keV. When we get up to 150 keV, you have to go close to 5 centimeters through muscle to drop by 50%. But still, that's, you know, giving us photons coming out the back of the patient, which is a reasonable number. Bone, on the other hand, you don't have to go far at all. It's less than half a centimeter at 30, but it's 3 centimeters at 150. So this is a graph of energy and the half value layers. And you can see that, as the energy goes up, it takes more sample to attenuate the object. This is why when you have a really big patient who comes in the scanner and they're a large person, 300-pound person, and you put them on the table, you usually crank the energy up to 120 keV just to get the photons through, right? Because otherwise you don't get enough on the detector, right? Yeah. Well, yes, and that's what creates contrast in images, right? They can. That's absolutely right. So you could say, if I wanted to make very precise measurements of the mu value inside this patient of the actually cortical bone, it's probably most susceptible to changes in density of that bone. And so you could model, say, look, I can make bone density measurements by looking at the actual values that I'm getting here. And other than patients' overall size is the most important factor when deciding what energy you're going to scan at. Because as the patient gets bigger and bigger, you usually scan at higher and higher energies such that more photons get through. Right? Okay. And remember, when we're talking about contrast, I said, there's a simple way of doing contrast. You take signal A on some object, signal B on another object, take the signal A minus signal B, divide by the standard deviation, and that gives you your contrast, right? And it's in units of standard deviation, right? So you say, oh, I've got 5 sigma contrast between these two things, right? In X-ray imaging, because the intensity is proportional to this equation, right? It makes sense to do this local contrast measurement where you take, if this is A, right, I get some signal A and I get some signal B and say, well, what's the difference between these two signals, right? We could do it that straight up way, but another way of doing it is say A minus B divided by the original A and ask what's the relative change in the number of photons that hit over here versus here. So you take A minus B divided by A, just plug all that in, and you get this, which is very simple, right? So basically the contrast between from A to B is just 1 minus whatever this little delta mu z is here, right? So it could be like 0.95 or something like that if z was really, really small. It gives you a percentage change in the signal intensity relative to the background, right? So this is used in CT quite often. So let's look at attenuation of X-rays along a path through the patient. This is where things get really interesting because it's not just a single type of tissue that our X-ray is going to go through at this point. It gets to sample a whole bunch of tissues on its path through the patient, right? So we'll say we have a source up here and there's a beam of X-rays coming through the patient along this line, and it's going to hit our detector down here, okay? So we're just focused on what's happening along this beam, right? And at any point, right, inside there, the incident number, the rate of change of number divided by the incident number along here is proportional to whatever the mu value is at that location, right, times delta x. So if you think about this, let's not think of it continuously, discretely. This is some delta x, some little unit of distance in the patient. I have a mu value across that unit. We'll say it's constant across that small unit. This is the equation that governs how many photons I lose in my pathway delta x through the patient, right? So I'm going to lose some, and then I move to my next delta x. I'm going to lose some more. I move to my next delta x. I'm going to lose some more. And the number I lose is going to be linearly proportional to whatever the mu value is at that point as I'm going through the patient, right? So if we take a look at our mu values as we're going through, if I come through here, and this tissue right here is muscle in the chest, then all my mu values along here are muscle. Then I might have to go through bone. I might hit a rib right here. So the mu value will change as the x-rays go through there. Now I'm in the lung, which is essentially air with a bit of soft tissue in it. So the mu value again changes a lot as it drops. So I don't attenuate many photons as I'm coming through here. I hit a vessel, might have contrast in it, mu value goes up. So that's the deal. That's my pathway, right? And to figure out the number of photons that come out the back and are going to get hit or hit my detector, it's the sum of all of those processes, right? So basically the number that come out the back of the patient or the number that went in the front, right? Integrated across all of these mu values, right? So I integrate that function that is mu as a function of distance along this line. And that's going to tell me my final attenuation number, right? If I want to do it, this is assuming that we've just picked an energy and we have mu for those tissues at that energy, right? However, remember the beam has many different energies in it. And so I really should compute this function for each of those energies, right? And then we would calculate what the intensity is, because I would remember the bigger energy ones would give a bigger flash and such. So to incorporate that, I have to know what the mu value is as a function of energy. So now I've got a tissue, let's say here we said that this was muscle in the chest wall. I need to know mu as a function of energy for muscle. And so I know that. And I need to know the beam that came out of my X-ray tube. I want to know the relative probability density of each energy. And then do this whole integral that involves integrating over all of those energies, right? That's a pain in the neck, right? And in fact, it's very hard to do it absolutely correctly because it's really hard to know this function for one thing, right? The manufacturer will not give it to you. You have to go in and try and measure it. There's a nice project, okay, for this is like design an experiment that you could run on a clinical scanner that, and I'll give you a hint, you would scan different materials, right? And you calculate what is this function from those measurements, right? It's kind of a neat little project, okay? But suppose we don't know. We know it's a blob, like the ones that I showed you. They all look kind of like that, but you would need to fit, you would go back here. It looks something like this, right? So you would need to break it up into like, I don't know, 8 chunks, and then measure how big it is in each chunk, and then fit a sensible curve to that, right? It's kind of a cool project. Okay, so this is the intensity I get on my detector for, this X-ray pulse. So the mass attenuation coefficients for some materials, here we go, and it shows you the difference. These attenuation coefficients are normalized to density. Okay, they're density normalized. So you want them basically such that if I had air and then I compress it such that it's really dense, right? You don't want the attenuation coefficient in your table, right? You want to be able to use that same attenuation coefficient. So it's normally normalized to density. So here's the relative numbers, right? At 20 keV and 100 keV. And you can see why it's easier to remember half value layers because these things, you're not going to remember all these numbers, right? And so here we have different materials and the linear attenuation coefficient of those materials as a function of photon energy. So here's bone, right? Everything goes down in terms of linear attenuation coefficient as the energy goes up, but they go down at slightly different rates, right? And so contrast between bone and muscle and fat, right, are slightly different here at 50 keV than they are over here at 80, okay? But for the most part, when we're calculating or doing a simulation or reconstructing an image, we basically say, we know that we have photons, between say 50 and 100 here, but we're just going to assume that all of our photons are at the mean at 60, and we'll do the math accordingly, right? As opposed to trying to do it in multiple dimensions, with energy being one of those dimensions. It does lead to some artifacts, which we will take up. Here's the addition. So here's our basic tissues, and this is the addition of a couple of new curves, which are contrast agents, okay? So remember, contrast agents have really high attenuation, linear attenuation coefficients. So they absorb a lot of X-rays. That's why they're here. So this is hypake, which is the stuff you inject in vessels to do angiograms. This is barium sulfate, which is what that guy was swallowing in the introductory lecture. And both of these have a thing called a K-edge. And so you have a linear attenuation coefficient, and then it suddenly changes when you cross a certain energy. And in this case, it's 33.2 keV. And what this means is the photons, once they're above that energy, they have enough energy to knock out a K-shell electron. They need that much energy to get that job done. If they don't have that much energy, that will never happen. And so once you get above that energy, you can start knocking K-shell electrons out. And so the linear attenuation coefficient changes for the material, right? Given that energy. And so that's called a K-edge. And this is the K-edge of barium is 37 keV. Here's an image of that stuff in the gut when you're looking for untoward geometries and things like that in the gut. This is, I go back to, yeah, here we go. So this is the liquid contrast agent that we're going to put in the vessels, and you can see it attenuates X-rays. Great. Here is an angiogram in the brain of a patient, and they've injected contrast and taken this picture. And the interesting thing here is that, as you can see, all of the background attenuation seems to be gone. And the reason that is they've obtained two pictures very close together in time. They first take one picture below the K-edge and one picture above the K-edge of this contrast agent. And so once they're above the K-edge, they get a very high contrast in the vascular structures. But anything that isn't this contrast agent looks exactly the same for those two energies. So you just subtract those two pictures, and all you have left essentially are the vessels. And it's called DSA, or digital subtraction angiography, and it's used a lot to image brains, specifically if you're looking for aneurysms and things like that. And so that's using the physics of this K-edge to get super high contrast. Okay, so what we're going to look at now is how you detect the X-ray once it's exited your patient. Okay, yeah.
Does the K value depend on the material which is being scanned, or?
Yes, yes, it does. So the question is, does this position of this K-edge depend on the material you are scanning? And yes. So you would design it so this probably has a K-edge that's associated with iodine. This is probably associated with the barium, this K-edge here, right?
For a bone will have a different KH than for
You know, I'm not sure, but it doesn't look like bone has a K edge on this graph, right? Looks like it's pretty smooth all the way down. So these are very pure ions, or you know, that we're imaging.
tissues like hydrocarbon don't have that.
I don't think so, no. It's particular to a certain atom. Yep,
The subtraction image you showed,
yep,
that's kind of inverse of what we normally see, isn't it? Like the higher contrast, the higher absorb, things that absorb more
Yep.
photons are
Yep.
normally white, right?
yep. So
That's
it's a good point. And if this was MRI, those vessels would be white. But digital subtraction angiography over the years, they just looked at them in this orientation and just kept doing it, I think. So it was just the preference of the radiologist. You can imagine just doing the subtraction the other way, you know. But like, I don't know why they look at it black. Probably because neuroradiologists, when they were doing angiograms in the brain without DSA, were just looking at the raw data, right? And probably they just looked at the dark vessels, right? And so once you've looked at 10,000 in one orientation, your brain has kind of trained to see things, right? We essentially are, you know, we're deep learning units. Like you just do it over and over and over again. And who knows how your brain does it, but really good radiologists, they'll look at something and they'll just see an abnormality right away before the rest of us have to scan through and go, oh, look at that thing, you know. So, okay. Up to this point, or up to about 2 years ago, commercially, all CT scanners used a material that basically caused a scintillation or a light flash when X-rays came in and were absorbed by the material. You tried to keep that light contained in a column by putting septa in the material. And so this was a detector element, you know, an X-ray would hit it and you get a flash, and you don't really want the flash to leak into here. You'd like it to stay in here such that the photodiode for this detector element went off and gave you a positive signal. Each one of these detector elements is on the order of 1 millimeter in dimension, okay, in both the Z direction and the theta or XY direction. Yeah.
So do they have to deal with like heat from when it hits?
Not really. No. If you're heating your detector up with X-rays, you got bigger problems, right? Because you've really heated up the patient, right? So yeah, so you don't want to work at that intensity. Yeah.
What's the need for that scintillation when you're getting a digital image out anyway?
Oh, the scintillation is the method by which you detect the X-ray, right? So without the scintillation, the X-ray goes undetected, right? So in this technology, which is 99.999% of all CT scanners in the world right now, and digital X-ray systems, the X-ray hits a material that has been designed to flash when an X-ray hits it, okay? And then after that, it's all light. And so all the technology after that is just photodiodes and all of that stuff, right? And so your voltage coming out of here, you know, it's sort of standard technology.
Light is read by the image sensor.
Exactly. The photodiode reads the light and it integrates up how much light is there. And so if it's a lot of light, it was a high energy photon, or it was a lot of photons, right? All at once, right? And this technology will be replaced eventually, like, you know, in 20 years, probably 50% of scanners will have what's called a photon counting detector in them. And what happens here is the X-ray comes in, it actually interacts with this material, the semiconductor, to produce electrons, not light, right? And so the electrons are like little pop of them, and they go straight to this detector here, right? And so it's voltage coming out of this thing, right? So the electrons come here and it's current, like direct current on your detector, as opposed to a photodiode integrating all the light, right? So you can imagine here you don't see septa, for one thing, because you don't need to worry about the light spreading through the entire detector or crystal, right? So what happens is the X-rays detected, these charges are created, and they just go straight to the diode here, right? And the nice thing about not having the septa is your efficiency goes up, because you don't have things dividing, your detector elements, right? And you get a much higher precision detection as to where that occurs. Not only that, you can determine the energy of the photon that arrived by the amount of current that comes out of this thing, right? If you're detecting them one at a time, then you know what the energy of the photon was that hit. So is it a 68 keV photon or a 1 in 20 keV photon, or et cetera, right? So now we have a spectrum of energies we can detect with our detector directly. So that's called photon counting CT. If people want to do projects looking at the difference between integrating detectors and photon counting detectors, that's something that's very topical right now. Yeah.
I noticed that you have like the pixelated anodes. So what kind of prevents it from like scattering inside the semiconductor? Like, so it actually goes
Yeah.
to the right hand.
Yeah, that's a great question. I don't know the answer to that. Like, I don't know why.
Is it just like fine enough?
If I have a X-ray detected here, it doesn't go to all of these. It just goes to this one. There's probably a depth. I'm not sure if this is drawn to scale. Right? They usually don't. Yeah. But this technology, every vendor, I think, has their own detector design. Okay, so it's a hot topic in X-ray imaging, is like making better detectors like this, these photon counting detectors. One of the issues with them is charge pileup. So if the number of X-rays starts to get overwhelmingly large, such that instead of this nice interaction here in a shower of electrons, I have 50 of them and a shower of electrons, then the charge piles up on the anode and it just can't detect anymore, right? It gets saturated. And so you need to make your detector work in a range where there's differential, ability to do that. So this is straight out of the Siemens website. So they have a white paper and everything in there. And there's a lot of papers that have been written over the last decade from physics labs, because a lot of X-ray physicists have been making their own photon counting detectors to prove the technology. And that's now moved into commercial production. Siemens has the first really workable photon counting system. It, I believe, is only, again, it's 64 slices instead of that 256 or 328 or whatever like that. Oh, sorry. So that's photon counting. This is the detection system for the system we have here, which is an integrating detector, traditional detector that has this fluorescent material on the surface. And this thing here is the anti-scatter grid over top of it. And so there's 128 detectors along here. You can see they come in little chips and they insert in here. Each one of these is 1, 2, 3, 4, 5, 6, 32, right, detectors along here in this direction, because this is 256 from here to here. And that's in the Z direction of the scanner. So we're looking sort of along the side. And then this is a two-dimensional scatter grid, such that when I'm sitting at a detector right in the middle of this thing, when I look up, I only see directly to the source, right? So you can kind of see the depth of the anti-scatter grid. It's pretty large in this case. Oh yeah, this I can't, wait a minute. You guys want to go see it on the web? Well, I'll let you do that, okay? Sorry. There it is. So there, if you go to this website here, you'll get some really cool animations as to how this detector system works. But we're in lieu of the time, we need to get going. Okay. Okay, we're done. Okay, so that's, you know, the sort of basic X-ray physics that we're going to do up till now. And now we're going to start looking at essentially linear systems, or the signals and systems aspect of imaging, to get some groundwork in, such that we know what we're talking about in terms of point spread functions and Fourier transforms and things like that. So any lingering questions about X-ray physics? It was a pretty fast shot through X-ray physics, but okay. So the slides for this have been posted for the lecture you're going to see now, and they haven't changed much, just tiny little changes. And the video from last year is here. Okay, so many sources. Okay. So this is essentially what we're going to visualize, right? Is a two-dimensional function. Okay, so X in this direction, Y in this direction. The relative brightness, or the number here, you know, the brightness as a function of position, is what we're going to call fxy. It's our function that we're trying to create, right? So it's an image, but in all of the math, we're going to call this image probably fxy, right? In 2 dimensions, it looks like this. In 3 dimensions, it can be just a Cartesian grid, you know, a block in 3D. And if we extract out a plane, we see our 2-dimensional image here. It has different dimensions in X, Y, and this is called slice, usually, is the Z direction. Oftentimes, for both MR and CT, X and Y, when the first images come off the scanner before you reformat them and stuff like that, most of the time, X and Y are sort of right and left, right, and anterior, posterior, and Z is usually, or slice is usually in the Z direction, right? Those are called axial images. This is an axial image. However, for both MR and CT, you can cut this up in any orientation you want, right? So it's a true 3D function, right? And so we're gonna, so first we'll just talk about what we're gonna understand at the end of this lecture, where we're headed with this. And what we really want to understand is how we mathematically describe 3 things. How do you mathematically describe the input to your system? If you want to know the properties of your system, how do we set up functions that are our input that's going in the system? How do you describe the picture of that input on the output of your system, right? And how do you describe the system itself? What the system did to this input to create this output, right? If this system, and I've built systems like this, where if you, regardless of the input you put in here, this is 0, right? Those systems exist. I have made them. They didn't last long. You move on from those systems, but that's a possible system, right? Other systems, like a little dot goes in, and what comes out, it's not a dot, but it's a blob. And it's a blob that might have sort of wings, you know, with oscillations out there, but it's not, you know, a delta function. So we're going to learn how to build input functions, right? Usually with Fourier coefficients, right? And in a linear way, we'll add up those Fourier coefficients to get a function here, pass that through our imaging system to figure out what the output image is going to look like. Okay. Once we have that, and we know what our input was, we can measure our output. At that point, we can mathematically describe what the imaging system is doing, right? And in very general terms, like, does it blur the object? Does it, decrease the amplitude of certain frequencies in our object, etc. And remember, a very important concept, we're going to review it because we already looked at this, but a super important concept is the point spread function. It's also called, and we'll interchangeably call it, point spread function and impulse response function. Same, if I say impulse response, that's what it means. It's the point spread function. And for CT, we had a little ballpoint out of the ballpoint pen that was much smaller than the voxel that we use to display pictures. And it produced an image that is a blob. Okay, and the width of that blob characterizes how much blurring occurs by your imaging system, right? And that's the impulse response to the point spread function. So how do you make mathematically this ballpoint pen ballpoint? So what is it mathematically? What's the best function to use to describe that thing? Well, if I put that ballpoint in space right at the origin and I go along the x-axis, it's 0, 0, 0, 0, 0, 0, and then for a very short period of time, it's non-zero, and then it's 0, 0, 0, right? So it's basically a rectangle function that is very high, right? It's got a large amplitude, right? And you can think of a delta function, and this is what this is how we mathematically describe this really pointy function, is that if I cut the width of that ballpoint, of the little bead, I cut it in half and then double its density, I get a higher function and it's thinner, right? And then do that again. So I get a much higher function and it's thinner again. So in the limit, as we get thinner and thinner and thinner, that function becomes a delta function, right? So it's the height of the function gets higher and higher as my width of that function gets more and more narrow until finally it's a rectangle that's super duper high and really, really narrow. And that's what a delta function is. This is really, if you want to look at the formal definition of what a delta function is, it's the function that when you multiply your image, okay, so I have an image which is fxy. It's a picture of anything just sitting there. And the delta function at the origin is the function such that when I multiply my image by that delta function and I integrate across the entire image, right, it pulls out the value of my image at one point, at 0, 0, right? So that's the definition of what the delta function does. It sifts out a value of your function at a specific point, right? And in this case, well, it happens at 0, 0, okay? By definition, that's what the delta function is. Okay, is there any questions about that? So the visualization of this is I have a picture, I have another function, which is a spike, right? I multiply those two functions together, then integrate, right? And it pulls out the value of the picture at that point. That's what the delta function is, okay? I think this was invented by physicists because it's kind of a weird function, but it's very useful for engineering and physics, right? But mathematically, it's a little weird. So here's oftentimes the delta function is graphically represented by something like this. You have the whole 2D plane. This is a two-dimensional. You can do it in 3D, you can do it in 1D. But this is a 2D plane, and you have this spike, right, at the origin. That's delta xy. You can offset the delta function from the origin just by, adding these offsets to the xy arguments such that the delta function hits 0, 0 out here, right? The argument for this function hits 0, 0 out here at psi and eta, right? So we can slide that thing around and see how systems behave as I, change my position in the picture. This is a special delta function that sifts out values along a line, right, in 2D. So basically all of the XY points that sit along this line will give us a positive value. And so if I multiply this by a function, I'll just get the function along that line, right? And that will be super important for CT reconstruction because we look at lines through the patient at different angles. And then this is a set of delta functions. And here's a, this is what in the book, this is the terminal or the notation they use, where you have the delta function xy and a definition of delta x and a definition of delta y, such that every delta x, you get one of these delta functions, every delta y, you get one of these delta functions. And that is called a sampling cone, right? So I could now sample my function at all of these different points by multiplying this and then doing an integral. Now I've taken a continuous 2D function, f, multiply it by this, integrate, and I now still have a continuous 2D function, but it only has values at where these delta functions exist, right? Everywhere else is 0. And so that concept, that function is really important when we look at sampling. It's like to actually sample f of x such that you could reconstruct what f of x was later, how many of these points do I need? That's one of the problems of sampling, right? So two other functions that we're going to look at a lot. And this as, these are tools. These are like the algebraic arithmetic tools that we're going to be using. One of them we use a lot is the rectangle function, which is 0 up to some, like, let's call it 1/2 from the origin. Well, it is 1/2. Then it goes to a non-zero value. Once it crosses 1/2, becomes 1. And then when it crosses, when it crosses -1/2, when it crosses a half, it goes back to 0. So that's called the rectangle function. And you can imagine that's extremely useful if you want to window something. So you have interesting stuff, but you're really interested in a certain domain. You can multiply by a rectangle function to get rid of everything and just look inside that window, right? And so that's what this is used for often. Yeah. Correct. Oh, that is a, oh no, I think this is the y here, right? No, what's he saying? 0 for x greater than half. Oh, okay. No, this is a typo, right? Yeah, you're right. Absolutely. That has to go in the corrections to the book. Okay. We already have a list of corrections for this first book. So yeah, it looks like, unless this is taken out of context, but because this says rect xy, right? And so I think what we're doing here is taking it out of context. We're only looking at the cut through the y = 0 plane here, but that's a good point. I'm sorry. We should cross this out for this diagram, cross out the y, cross out this y. Okay, we'll correct that in the slides. Or we'll make this a 2D function, which I think comes up next here, right? So, okay, nice, good point, right? This just didn't look just like, what is going on? You got a 1D function and there's 2 arguments. Okay, good point. Okay, you can make it in 2D just by having, it's a unit square, right, in the plane, right? And it goes up to y½ and y -½. But anyway, okay, let's move to the next function, which is called a sinc function. And the sinc function is like a sinusoid. It oscillates, right? And so it oscillates here with, frequency 1, right? And it decays away as you move away from the origin. Okay, so the height of these peaks are decaying away. The function is decaying away by this term, but it's oscillating with a frequency defined by this, okay? Interestingly, as it goes to 0, right? As x goes to 0, it does not blow up, right? It reaches a limit, right? As we get closer to 0, because x and sine x both go to y equals x as they come to 0. And so you get 1 at that point, okay? This function is used continuously. I mean, we use it all the time as we do with this. And as fate would have it, if you take the Fourier transform, we'll see this, of this function, this is what you get, right, in 1D, okay? So it's, for MR especially, when you're bouncing back and forth between space and Fourier space, knowing some of these transforms in your head is very important, and this is a primary one, that a rectangle function gives you this in Fourier space. And we'll talk about that in a minute. Here's a two-dimensional rectangle function, right? Which is the product of two one-dimensional rectangle functions. And when you look at its Fourier transform, you can create a two-dimensional sinc function, which is just the product of two sinc functions, one in x and one in y. And so that kind of looks like a sombrero function in a way as it's going out. Okay, so everybody knows about complex numbers. We're going to use them a lot, especially in MR, and where we describe the value of a function by its magnitude in the complex plane, where this is the imaginary direction, real direction, and its phase angle, theta. And you know, these are used throughout signal processing because it's important to understand. Well, it's very useful in looking at things that are dependent on phase, really, because you have these phasors. And so here the amplitude of this thing is just, you know, the Pythagorean amplitude at √5, and the phase angle is the arctan of the ratio of the y over x. Complex numbers, you know, defined J if you're an engineer, I if you're a physicist. When you square it, you get -1. You can use them just as they are with any normal number. Just whenever you square the thing, you get -1. And so this, you know, just by multiplying as you would any numbers in parenthesis, you can get a real number here. This is 3 plus 2j, 3 minus 2j. When you multiply them together, you get this number. So this is the relationship between a phasor in the complex plane, e to the ji, and cos and sine theta. So this relationship here is often thought of by many mathematicians as like the nicest equation in the world, right? The most remarkable equation in the world, that it works out this way. And when you look at it and you say, well, wait a minute, e to a complex, you know, argument, why would that have e is the banker's number? Like it's 2.718964, right? And e to the x is just an exponential growth. So why would it have anything to do with cosine and sine, number one, right? And what's the relationship between the phase angle here and the phase angle up here? And so when you're looking at where this comes from, if I have a unit circle in the imaginary or in the complex plane, so I have a length of 1, this number, e to the j theta, has cos theta as its real component and sine theta as its imaginary component, right? It still doesn't tell you, like, when you're just looking at it in its raw form, like, what is the relationship between e and cos and sine, right? But the one hint, I think, is that e to the x like is a function that when you take its derivative, it's its own value, right? So that's a very special function, right? When you do differentiate it, you get the function back. So it's infinitely differentiable, right? And so is cosine, and so is sine. So when you take the derivative of cosine, right, you get negative sine, take the derivative of that, you go back to cosine, negative cosine, take the derivative of that, go back to sine. So it is infinitely differentiable as well. So the two sides of this equation are behaving the same in that way, right? That you can imagine it. And then when you write out the, power series expansion of cos x and sin x around the origin, see a very interesting pattern, right? In that when you're looking at cos x, you start at 1 and then it decays down, obviously, and you decay by you drop by a certain amount, go up by a certain amount, drop by more. And when you look at the sign of these terms, x squared, you get a minus sign, and then x to the 4th, you get plus, and then x to the 6th, you get a minus sign. And so I need something that's going to flip the sign every other even term, right, to make this series work, right? So what the heck is that? I need an item that flips the sign every second even term. And you go, oh, I've got that. That's I, right? Or J. That thing, that's the periodicity of J when you're putting it to even powers, right? So that's another reason why you can think that this relationship works, the Euler's relationship. But what we're going to use it for a lot is as a phasor, which is a unit vector, and it's basically spinning or in the complex plane with different rates, okay? Plane waves are another thing that you need to be very comfortable with, specifically in MR. And so this equation, I'm sorry, it's really small here, but where we have a function of brightness in the plane, so our fxy is the sine of this argument, and there are two terms in this argument. There's a product of mu naught in x and a nu naught in y. And if we look at what this function looks like in the plane, in the xy plane, as we change these two values, the mu naught and u naught. So if we set this one to 1 and this to 0, we get a sine wave, right? A full cycle sine wave, if that is 1 here, in x, and it's constant in y. Right? So it doesn't change as a function of y. It's just we have a plane wave that's going along in x. If I double this constant value here, then I get 2 full cycles across, let's say this is 1 centimeter. If I make it mu4, then I get 4 full cycles across. And so just by changing this number, this argument here, I'm changing the frequency of these plane waves. When I start changing the numbers here, right? So now I have 4 and 1. We get 4 cycles if I go just in this direction. However, now, as you can see, what's happened is with the 1 cycle in the y direction, it looks like a plane wave that's just shooting off in a different direction, right? So we've rotated this plane wave in this direction. Again, if I add 2, we rotate it, it goes up this way. Go to 4, rotate it, goes up this way, right? So now when you project on the x and y axis, you get these frequencies, but it also has a oscillation as it's going off on y equals x, right? So this is the fundamental relationship that occurs in MRI, in the sense that when you prepare your sample to listen or take signals from the sample, the first thing you do is you impose one of these relationships of the phase of the signal on the sample. You get this picture set up. You can imagine your brain or something is sitting in that field of view. You impose this phase shift on that brain, right, using gradients and things like that, and then you listen to the signal, right? And you get this set up first, and then you listen to the signal. And so you're multiplying the actual patient by something that looks like this, which is pretty cool. What did I want to say about this? Well, this is just a description of a 2D phaser, right? Where we have that mu and u argument is the frequency of the oscillations of that function in the different directions. And, oops, sorry. Here you go here. So this function here, right, is essentially what you're going to be seeing in magnetic resonance over and over. Okay, the output of a continuous system. So in the book, they use this script S term for our system. We're going to just use bold S because I don't have this on my computer. So here's our image, or this is actually, I'm sorry, our object, right? So it's sort of the ground truth, underlying true object that we're looking at. And then we capture it with our system, with our imaging system, and this comes out as our picture, okay? So f of x, xy can be some beautiful pattern I put on the wall. I know precisely what the pattern is. I take some image of it and I get this, right? And we would like to describe what this thing is and what it does. And so algebraically, this is what that looks like. And we'll do one definition before breaking, and that is, what is the definition of a linear system? So if I have my imaging system S, and this relationship holds, it's called a linear system. So let's break this down piece by piece. I can create a ground truth signal fxy by adding up different components of fxy. So suppose my final fxy is the result of a set of k images that are added up together with these coefficients, relative coefficients. So now I get a final image, which is fxy, but it is the sum of all of these sub-images that I've made, right? So it could be one sombrero and then a sombrero with a much narrower peak, right? And then a linear function. I add all those together, that's my picture. So if I can break down the picture that way, they're just a linear sum, right? When I take a picture of fxy, the whole thing, if it turns out that it's equal to doing this, which is taking a picture of each individual component of my summated image, and then multiplying those by the same weighting coefficients, right? So it's fundamentally different, right? I've taken k images at this point, and I sum them together with these coefficients. If that equals what I get when I sum up the pictures and take a picture with my system, then that system is called linear, right? And this property makes life remarkably simpler when you are trying to manipulate systems and images, if this is true. If you can just separate out different sub-pictures, like through sums, and you know that when they're all added together, you'll produce the same picture, right? Is that getting in there? Okay, good. So that's called linear. So here we'll go back to our impulse response function. And this doesn't look like a dot, but assume this is a tiny dot, right? And I can now create either a point spread function, same as the impulse response function. But when I move my dot here, right, by changing the position of the delta function, right, with psi and eta. So I change if I need a new point spread function, to describe what happens when a dot comes in from this location versus this location, right? If I have to generate a new impulse response function for something up here, then that system is not shift invariant. That means I need a whole set of point spread functions. And they're a function of, X and Y, but now they're also a function of where I am in the plane, right? Psi and eta. And in optics, this is, if you've had a set of cheap binoculars, or when you're a kid, you had a really cheap microscope, you know that those systems are not shift invariant, right? You need to put the lens right on your target, because if you go off to the edge a bit, it starts to blur, right? And so you have a different point spread function depending on where the object is in the field of view, right? And if that occurs in our CT scanner, such that my little ballpoint pen right in the middle of the scanner versus way off at the edge of the scanner produces a different point spread function, impulse response function, then that is not shift invariant. Okay. And most of the time when we're doing arithmetic / mathematical analysis of images, we will multiply by a two-dimensional rectangle function to put us in a situation where we can make this assumption, right? Because it makes life a lot easier. If you don't care where the object is in the field of view to get the same point spread function. Okay, so I'm going to stop there. We'll start there on Wednesday. Okay.